Hello, everyone. This is Konstantina. I'm a research engineer in Google, and I'm very excited to be here to talk to you about recommendation systems. Specifically, I will be talking to you about how we can drive a better user experience via the reward function of reinforcement learning-based recommenders. So before I begin, I just want to give a huge shout out to all my amazing collaborators inside Google, without whom this work wouldn't be at all possible. So what I would like to do in the next about 5 minutes would be to give you a small overview of reinforcement learning or RL-based recommenders. Specifically, why does it make sense to model recommendation as a reinforcement learning problem? The idea and the mental model that you should have during this talk is that recommenders are essentially these user-in-the-loop systems. Effectively, you have from the one side the recommendation system, which is this agent deciding which kind of content to show to the user. And from the other side, you have the user interacting with these items recommended by the agent and providing feedback indicating how much they enjoyed their experience with them. And so then this feedback is being taken back into the recommendation system, which is updating its beliefs about how much this user enjoyed different items, and in general, what are these topic preferences of the user and what they might enjoy to do in the future. And so all this user-in-the-loop story here makes recommendation systems an ideal fit for modeling them as an RL problem. Specifically, throughout this talk, I will be using this case study of a large-scale recommendation production system where we have access to these log trajectories indicating in the recent past history, how much did these users interact with different items and so on. And the idea is, given this trajectory, what can I recommend to this user next? So we're operating in this batch reinforcement learning, given that we have access to these batches of log trajectories, and we will be using this reinforce agent. So the agent is this candidate generator deciding which candidate items to show to the user from these millions of items that you have in the corpus. And then you want to decide this, what item to show to the user, given some state representation, where the representation is going to capture the user interests along with the context. And given the fact that both the context and the user interest could be changing over time, we're going to represent them via a recurrent neural network. Now, the action is going to be which one of the items from the millions of the corpus to nominate to that user. And the reward, which will be the thing kind of guiding the learning of the policy, will be some indication of the user utility. So one important aspect that I want to highlight before moving on to the reward is the fact that the policy that is used to collect these log trajectories could be very different from the policy that we're learning. And so it's important to make sure that we do off-policy correction to account for this training serving skew. And so for that, I totally recommend this awesome paper on top K off-policy correction. However, during this talk, I'm not going to be talking about it because I want to pay more attention into the reward. So what is the reward? Imagine that you have this policy network parameterized by these parameters theta, and your goal is to find these theta parameters so that you can maximize this expected cumulative reward. And so the idea is that the reward will be the thing guiding you to decide between an item A versus item B, which one to recommend. And so the way you do that is you look at the trajectory happening after these two items, and you consider these specific proxy reward signals accompanying these different items happening in the future trail. And so then you can compute this discounted cumulative sum of these future reward proxy signals. And when looking at what is this reward for item A versus item B, you can select the one with the larger reward. Now, one thing to notice is that typically recommendation systems use behavioral and objective ratings as proxy reward signals. However, the main focus of this talk is to say that what users do, which is the thing captured by these behavioral signals, is not the same as user utility. And so we want to highlight that reward shaping is this very effective tool that we can use to make sure that we align the reinforcement learning agent objectives with the user utility. And so now let's move on to the main part of this talk, which is what are these aspects of the user utility that we want to capture into the reward, and which are not right now captured just by using these behavioral signals. And so that aspect is going to be what users say. And effectively, we will be using survey data to capture the user satisfaction. The key idea being that what users do on the recommender platform could be completely orthogonal to what users say they want. And so you want to have some way of capturing that. And the way to capture that is by having this qualitative data, asking users, how would you rate your experience with this following item that you've recently interacted with? And then this item could be selected at random from your recent interaction history. And then the user is supposed to answer to this survey, for example, in a scale of 1 to 5, or smileys, or yes, I love this item, or I hate this item, and so on. And this survey is going to appear on your feed while normally you will be consuming different items that are recommended to you. Now, as you can imagine, if you want to utilize such qualitative data in order to be able to capture user satisfaction, you're going to run into certain challenges. The very first challenge is, given the fact that the recommendation systems are primarily for content consumption and not for asking users how they felt about different items, you're going to have a very small percentage of the item corpus to have associated surveys. Furthermore, even if you did show a lot of surveys, very few users tend to respond to these surveys. As a result, you have a big sparsity problem. And what this means is that if you then want to utilize this reward, as we said before, to be this cumulative discounted sum of what are the reward proxy signals in the future trail, and you want to consider both the behavioral signals and these satisfaction signals based on the survey, you will not be able to just do that by just simply combining these two sets of signals, because behavioral signals are going to be much, much denser compared to the satisfaction signals. And so how do you address that? So the idea that we have here, and that I'm going to be guiding you through in the next few slides, is that besides our policy network, which will be deciding, given the state representation, what item to show next, we want to have this satisfaction imputation network, which we will call the critic network, which will be imputing for each user item pair what is their satisfaction. And then we'll be incorporating that into the reward. So before I guide you through the critic network, let me first introduce you to the policy network and its exact parameterization. So the idea is that, given that we have access to these log trajectories of these, capturing these interactions of the user with the different items, we're mapping this sequence to this recurrent neural network, which then the output is going to capture this state embedding representation of the user, which could be changing over time. And then we concatenate the state embedding with some representation of the context, which could be the time of the day or the device the user is using, and so on. And then if you concatenate the two and you pass them through nonlinearities, then the idea is that you will be mapping them to what is the softmax over the entire item corpus. And this way, you will be predicting what is the next item to show to the user. Now, on top of that, we want to build this satisfaction critic network, which the goal of which will be to say for each user and each item pair, what is the survey response, which, as we said before, the survey response will be an indicator of the user satisfaction with the item. Now, as we said before, the challenge is sparsity. And so in the batch, where you have these different, let's say, the interaction of a user with the item, only a few of them will have an associated survey response. Having said that, we will be training the satisfaction critic head only on these very sparse survey responses. And the way we're building this network is to utilize this state representation captured by the RNN associated with the specific time that this user actually interacted with the item on the survey. And you concatenate that with some representation of the item and of the context around that survey response. And so using this as input, you can then map that to what is the survey response given in your data. And then you can utilize that as an imputation model, and you can predict for each one of the interactions that you have access to in the batch, what is the corresponding imputed satisfaction. And so now we can change the reward, and instead of being just the behavioral related reward, it can be the multiplication of this imputed satisfaction reward along with the engagement reward. So before I guide you through these different live experiments that we did to showcase the value of this satisfaction imputation, I want to first guide you through some learnings that we had while trying to build a good satisfaction critic network. So while I do that, I want to highlight a few challenges associated with this data. The first challenge, besides the sparsity that we already highlighted, is the fact that the labels are very imbalanced. As you can see on the pie chart on the left-hand side, the majority of the labels that we have access to are 5-star responses, versus, for example, the 1-star responses capture only 4.8% of our data. So what this means is that it's very important to balance the data so that both these responses capturing a more negative user experience are given an equal focus, with these responses indicating a more positive experience. And so on the right-hand side, what I'm showing you is the fact that the accuracy of the critic network is significantly improved when we are weighting these negative responses, which in our cases are the 1, 2, 3 stars, by 3 times more compared to the 4s and 5s. Furthermore, I want to highlight what are the different features that we used and that we found that are pretty predictive in being able to say what is the satisfaction level of a user with an item. So first of all, I want to focus on the item-related features. So you can see here that we utilize features capturing the time spent in seconds on this item, some discrete features like, for example, the item ID, the creator ID, and so on. And what we found is that by using the set of features capturing the item instead of each one of these features or a couple of these features led to a pretty big jump in performance of the critic network. Furthermore, we found that the user state representation as captured by the recurrent neural network along with this context embedding gave a more good predictive quality compared to just using the item-related features. Now, a further challenge, which is pretty important to highlight, is the fact that the satisfaction data are inherently biased in the sense that you can see here on the y-axis the response rate and on the x-axis the survey score. And you can see that the higher the survey score, the higher the response rate. And so what this means is that users are more likely to respond when they will respond they actually like the items more. And so if you think about this in a causal framework, what this means is that if you just utilize survey responses in your data, as I showed you before in the satisfaction critic network, then the causal network would just be this bottom part of the chart. So it would just be the survey responses. However, the causal story is more complex. So in reality, what you have is you first have access to the survey impressions. And so then, given the survey impression, the user actually decides whether they want to respond to this survey. And only if they do, then you get to observe the survey response. And so you can see that there are these confounder latent variables Z that are affecting both the decide to respond variable and the survey response, meaning that the survey response is actually biased from the deciding to respond variable. And so it's very key here to be able to deconfound the survey responses from the response rate bias. So how do you do that? Ideally, you would like to have access to some intervention where you would externally set the decide to respond variable to 1. However, this is not feasible. And one popular then way to be able to debias your data is by using inverse propensity weighting. The idea of inverse propensity weighting is to make sure that you have some pseudo-population where the target variable that you care about, which is the survey response, is not going to be biased, is not going to be confounded based on the response rate confounders. And so the way you do that is you want to build this propensity model, which will be predicting what is the probability of seeing certain data points in your data. And so what I show you here is that, for example, here I show the simplification of a satisfaction critic network, where you just have these user features, item features, some cross features capturing the two, and then you map those through nonlinearities to capture what is the survey response. So on top of that, you can build this propensity model, which is going to predict what is the probability of a user actually responding to the survey. And this response tower is going to be built, is going to be trained on the survey impressions rather on the survey responses. And so both of these towers will be trained concurrently, and you will be using the predictions of the response rate tower in order to weigh the examples of the survey response tower. Specifically, you will be weighing more the examples that have lower propensity to respond and less the examples that have higher propensity to respond. And this is a technique which is being shown that it's actually going to give you an unbiased estimate of satisfaction. Moving on, I want to guide you through these live experiments that we did, where we compared the control, which is this policy network that doesn't have satisfaction at all into the reward, with the experiment, which is exactly the network that I presented to you a couple of slides ago, where I was showing you that we have the policy network, and on top of that, we have the satisfaction critic. And so what you can see here is what is the histogram of satisfaction scores across nominations. And you can see that the blue bars, which are representing the experiment, are much more shifted towards the right, where the right captures higher satisfaction level with the items. And so that's exactly what we want, because we expected our approach to actually improve the user experience and the satisfaction level of the user with the different items. Furthermore, you can see here that these are for live experiments. What is the percentage change of satisfied engagement of the experiment, which is our model, versus the control, which doesn't have the satisfaction imputation part. And you can see that we significantly increase satisfied engagement, while at the same time, we significantly decrease unsatisfying engagement. And so that's a pretty good evidence to show that reward shaping can be a very effective tool in order to be able to align the reward of the system with the user satisfaction and with what users think are satisfying about different items. However, user satisfaction is not only enough to be captured in the reward. For example, you could care about in your recommendation system to make sure that you do what is good for the user, but also what is good for society. And so an important aspect that is worth thinking about is how can we incorporate social responsibility into the reward. And of course, here again, you run into many challenges which could be similar to the satisfaction data that I talked to you about before, but even more challenges. Like, for example, what captures whether something is responsible or not could be a very noisy signal. Also, typically, these signals could come from a model. So you basically have this model uncertainty around these responsibility-related signals. And also, there is this inherent trade-off of saying, what is responsible engagement versus non-responsible engagement, and how much are you willing to sacrifice the one for the other? Having said that, what we did here is we did again a reward shaping approach, where we wanted to consider, along with the behavioral signals, different signals capturing the misinformation quality score. And so what we do is that, as we mentioned before, after an item, you're looking at the future trail, and you get to see what are the corresponding reward proxy signals that you have access to. And so at each time step, besides just using behavioral signals, you will be looking at the misinformation quality score. And then a reward that we found that was very successful in being able to reduce misinformation and increase responsibility was a reward where we multiplied this discounted behavioral related reward with this term of 1 minus the maximum misinformation quality score in the trail. The idea being that if you have two items, and then the one item leads to a trail with much more misinformation compared to the other, or for example, some other notion of non-responsibility, then you want to effectively penalize more that item, leading to more misinformation or more non-responsible engagement. And what we found in live experiments is that if you compare this approach with this policy network where you do not consider this responsibility part into the reward, you can see that with our approach, you can actually significantly decrease the impressions, the recommendation impressions with high misinformation score. And furthermore, although one would think that you would necessarily have this trade-off between responsible and non-responsible engagement, in our case, we found a win-win. Effectively, we found that by foregoing this non-responsible engagement, we can actually increase responsible engagement at a rate of 1 to 19. And so this is a further learning that we have here, that again, reward shaping can be very powerful in order to be able to align the reward and the objective of the system with what is good for society, where here I mentioned that as responsibility. But again, I think this space is very much scratched just on the surface, and there is much more work here. And so, are we done? What are these future challenges and opportunities that we have ahead of us? So I think so far, the main takeaway that I wanted to highlight is that indeed reward shaping can be super important in order to be able to align the system objectives with the true user utility. Having said that, the approaches that I described to you so far, they're focusing more on handcrafting the reward. And so the idea there is that if you incorporate more and more objectives, eventually you will be leading to a more complex reward. And so instead, there could be a better way. For example, there is this inherent part here that the users are learning their preferences while they're interacting with the recommendation system. And so you can actually, instead of trying to do that top down, and you get to say that the reward of the system is going to be this, you can effectively infer the reward from these imperfect actions that you have access to. And so this leads to a framework of inverse reinforcement learning that we could borrow from the robotics literature, which I believe could be a very fruitful area for recommender systems. Also, another part which I believe is very interesting is capturing the different causal factors into the reward. Like, for example, certain signals could come first and could affect other signals. And so there could be some causal network that you could capture here. Furthermore, as we said before, the reward, besides capturing good things, like, for example, high satisfaction, it could also capture these negative constraints that you want to have in your systems. And so the area of safe reinforcement learning could be very interesting to look at. And finally, given that we have all these different objectives that are in an interplay here, like, for example, you have engagement and behavior-related signals, you have satisfaction, and then you also have responsibility, and there could be more. It's very important to do more research in multi-objective reinforcement learning. So all these areas are areas that we're super excited about and that we are currently doing work on. So if you're interested, we will be super happy to hear from you. Thank you so much.